In this example, we're going to take some actual values for the lower limit a and the function f of t in that strange g of x function defined in the fundamental theorem. Here we're asked to find the derivative of g of x equals the integral from a to x of 3t squared plus 7t plus 9 raised to the 1/2 power dt. Okay, so you see that this looks so much like that integral function in the fundamental theorem, but we're letting a, the lower limit, equal 0, and we're letting f of t equal 3t squared plus 7t plus 9. Well, let's check. Let's see if it's even possible for us to use the fundamental theorem, part 1. What does part 1 say? Part 1 says that if little f is continuous on the x interval from a to b, that implies that the derivative with respect to x of this strange integral from a to x of f of t dt is indeed equal to f, the little f, evaluated at x, whenever x is on the interval from a to b. Okay, you should pause right there and think about that. Let that sink in. What we need to do is show that our little f is continuous. Then we'll be able to apply this theorem. Well, what is little f in the question that was given to us? Here, it's given to be the 1/2 power, so it's a square root of 3t squared plus 7t plus 9. We want to see if that's continuous on our interval from a to b. Well, the radicand, the stuff under the radical sign, 3t squared plus 7t plus 9, that's always going to be greater than or equal to 0. You can see by just looking at it. So that means that it'll always be greater than or equal to 0 for all real numbers t. So we're never going to get a value under the radical sign that's negative. And if we had, that would be an area where it would be non-continuous, discontinuous. But it doesn't happen here, so our even index root f of t is indeed a continuous function. It's continuous for all real numbers t, so indeed it's going to be continuous for any interval of x. Okay, so we have decided that we are allowed to apply the fundamental theorem part 1 because we have a continuous function little f inside the integral. Thus, the fundamental theorem, part 1, says, well, I'm just going to repeat what's in the cloud. I'll say it with more words. The derivative of what we call g, look back at what we called g, is equal to g prime of x. That's a way of writing it. Another way of writing that, d dx of g of x, which is, replace g of x with what we have. It's d dx of the integral from 0 to x of 3t squared plus 7t plus 9 to the 1/2 power dt. And that is equal to, well, let's go back. It's actually equal to f of x. Oh, because that's what it says in the cloud. That's a fundamental theorem. Specifically what it says is it's equal to d dx of the integral from 0 to x, or I should say a to x, f of t dt. Okay, so that's 3x squared plus 7x plus 9 to the 1/2 power. Ooh, wait a minute. What did we just do? We showed that the little f in the given integral, it is the integrand, the function that's being integrated in the given integral. It's 3t squared plus 7t plus 9 to the 1/2 power. We showed that that little f of t is continuous. Once we had established that, we applied the fundamental theorem in the cloud. It said that the derivative of that thing, of that entire integral, which was named g of x, the derivative with respect to x of that entire integral is equal to little f, which is 3x squared plus 7x plus 9 to the 1/2 power. Well, there are so many notations here. Let me just restate this really briefly. It says, what we've done says, in other words, that here's how you could say it. The derivative with respect to x of the integral from 0 to x of 3x squared plus 7x 3t squared plus 7t plus 9 to the 1/2 power dt is equal to the evaluation of the integrand with respect to x, 3x squared plus 7x plus 9 to the 1/2 power. Now, what I just wrote at the very bottom, that is very important. So you just take a minute to look at that bottom cloud and see if that's registering with you, because that is really the crux of this entire problem.